And he'll take it over.
Fantastic.
Jonathan.
Thank you so much. So hi, everybody. I'm Jonathan Valamehr. I also go by Johnny. I'm one of the founders of Tortuga Logic. So we're a hardware security company that provides different pre-silicon security verification services and tools. So hardware security is very near and dear to my heart. And we wanted to put this panel together because there's a lot of talk about attacks and these sorts of things. But I wanted to see what people are doing on the defensive side and what people are actually doing to protect against a lot of these attacks from the ground up. And so that's why we put this panel together with some awesome folks. So the format of the panel will be, we'll talk up here for about 35 or 40 minutes, and then we'll open up for Q&A for everybody. So great. I'm going to introduce the folks on here. So first we have John Callas, who in the past was a co-founder of PGP and Blackphone, as well as security at Apple and other places. Presently, he's Senior Technology Fellow at the ACLU. And it says here he likes sports cars that work on physics alone. John, I feel like my car works on physics alone, my Mazda, but maybe you have a different opinion?
Yeah, I was thinking, hydraulics and gears and things like that. Yeah.
That's a good question.
What was the question?
As opposed to what?
As opposed to being computer controlled and so on and so forth.
So this is like carburetors and diesel.
Yeah. Or I'll go for fuel injection.
Oh, will you?
Yeah.
How dare you? Mechanical fuel can overclock that.
Well, welcome, John. Next we have Mr. We go down here. Perfect. We have Joe Kiniry. Right, Kiniry. Dr. Joe Kiniry. And you already introduced yourself in the previous talk, but as a reminder, he is a principal scientist at Galois and the principal CEO and chief scientist of Free and Fair. I don't have any fun facts for you, but if you want to throw one out there.
I'm tall and bald and loud.
Okay, good. Fantastic.
Thanks, John.
Next, we have Robert Van Spyk, who is a leader in hardware security research within NVIDIA's security architecture team. Prior to NVIDIA, he was the first security analyst hired to establish Riskier's North America Security Lab and a resident expert in chip security, mobile device security, and fault injection attacks. He has given a side channel and fault injection training at Black Hat focused on embedded systems. And it also says that Robert has done research in the biomedical and biohacker fields. Robert, are you a cyborg?
I am not a cyborg.
Okay. What does biohacking mean to you?
To me, and people should be really careful with this. I grew up doing hacking, modifying code, figuring out how things work. Actually, that's a big part of it. Reverse engineering. So a lot of biological science is actually just reverse engineering life. So that's kind of my take on it. I'm not a cyborg yet. I don't have any implants
yet.
I've designed implants. Someday I might get there, but only when I'm 100% sure everything is legit and safe.
Fabulous. Okay, thank you. Next, we have Shawn Hoffman from Microsoft. It says here, as part of the offensive security research team at Microsoft, Shawn discovers and exploits vulnerabilities throughout Microsoft products, focusing on low-level software and hardware. The team uses the resulting information to drive new defenses and mitigations. Very cool. Any fun facts from you, Shawn?
Not really, no.
Cool. And lastly, we have Christopher Harrell, is it? From Yubico. So, Christopher, who previously spent time securing a wide variety of things at Yahoo, Apple, and other companies, is currently the EVP of Global Engineering and Technology at Yubico. He likes learning about other people and cultures and trying to improve lives with highly usable, safe technology. Very good.
Sounds super boring, right?
Awesome. Fantastic. So I will, I think you guys can just pass the microphones around, whoever wants to start off. So first question I have is, how would you describe the current state of hardware security?
What would you like the answer to be? I mean, I could tell you how it's horrible. I could tell you how we're doing a good job.
Tell me the truth.
It's both at the same time.
It's both at the same time.
The biggest challenge that we have facing us is that in a lot of cases, hardware is software. Yeah. And so we inherit all of the problems of doing software when we do hardware. And that even goes back to my smart ass remarks about automobiles, which is that when a device has in it a Linux kernel and boots it up, and yet you think it's a piece of hardware, it's going to have a set of capabilities and vulnerabilities that you wouldn't have even imagined.
I totally agree with that. Yeah.
Now, on the other hand, it used to be that one of the prime rules of security was that physical access is all. And it was, even in terms of discussing how you would do security of hardware, if it is in your adversary's hands, game over. And we have made in the last 5 to 10 years such amazing gains on having devices that are consumer commodity hardware. If you look at any of the top-end phones from Apple or Google, you will see that they are surprisingly resilient to anything but a nation-state attack. And they cost what consumer hardware costs. Yeah. So this is a huge advantage and shows that things are not all despair and that we can win.
Yeah, I was going to say companies that are hiring great people and spending money on security are creating great consumer products, one of which is in my pocket. My friends at the Apple team in particular have been doing quite remarkable work. If anyone wants to say
I would agree with that. I think in general, there was the hardware security dark ages, and we look back at that and think how naive all of those designs were. They were really going for performance, cost area, these constraints that were enormous concerns back in the day. And just like, developers who are working at the software layer, they don't think that the hardware can betray them. People are starting to learn that this is the case. Especially Joe Fitz, he's been showing what hardware attacks can do if they don't understand what's going on under the hood. And I also agree that there's a number of companies that have, through all sorts of technological solutions, and this is everything from like automation, formal analysis, really well-equipped, expert red teams. They managed to kind of close the loop and get rid of so much of the attack surface, so much of the vulnerable code. And kudos to them. I think in a lot of areas, I would call them like markets that care about security, that have been embarrassed in the past. They are getting to the point where I would want them to be.
Yeah, that's a good point. I'm not sure if there's anything left to say, but I guess to make it a little less rosy, while the markets that have been affected in the past or have some reason to learn from mistakes have definitely been getting better. I would say that there's still the issue of upcoming products relying on older technology or things that are like IP that's taken from third parties that you still need to be vigilant about. So
I'm just excited because there's been an awakening. It used to be the case, as John said, that when you had a computer, the way that you secured it was with guards and dogs and guns. And then came local networks, and eventually came the internet with everything connected to everything. And to me, the big difference between then and now is that more interesting things are online, which raise the stakes a whole bunch. Obviously, we've had a bunch of sort of mini disasters or even large disasters, but that has awoken people to the need to do something about this. And so I'm excited that there's attention on it. I'm excited to see improvement. There is still a very long way to go.
Fantastic. Thanks, Christopher. So my next question was going to be about how we make security a first-class design constraint, but it sounds like you guys are pretty optimistic that that's sort of becoming close to that. Is that true?
We can start at the other end.
I think for me,
we all have to speak.
For me, it's about incentives. I think one of you two mentioned that it depends on the industry, it depends on past experience, it depends on the expectation of whether we think in that particular product or that particular line of business, it is advantageous to do that. Mm-hmm. So the places where there's a built-in bug bounty, like cryptocurrencies, crypto assets, crypto exchanges, they've learned some painful lessons and are starting to get better. In places that are making light bulbs, they probably haven't figured things out quite yet, because those incentives haven't hit them. But I think over time we'll see some trickle down and some different availability of IP and products that can help with that. But it's still in the early phases.
Got it.
The concern I have is that at the moment, given the paucity of experts and the lack of modern automated tooling, only the bigger entities that have the cash can afford to do security. Mm-hmm. I mean, if you're an SME, a small to medium-sized business building, say, a pacemaker that needs to be federally certified under the new standards, you just can't afford to do it right, given the lack of quality tooling and large numbers of experts. So learn more. You make a higher salary.
To kind of add to that, one thing I've noticed over the last year or two have been basically secure microcontroller, secure chip manufacturers have actually been doing value add through software. So I think what they noticed is the chaos in the IoT space. And they said, okay, we can fix that. We can give you a software stack that's more secure. Just use it, and it will work much better than your homebrew. And on top of that, we'll also give you infrastructure, which will take care of a lot of problems that you're going to face otherwise.
I think your tooling comments right on too. Even the big guys, when you see like the Nintendo Switch hack, for example, just misconfiguration of a NVIDIA register, that should have been caught by verifying that the design met the constraints of being secured before shipping. But, some human missed that. Tooling could definitely have helped.
Absolutely. Cool. Now, one thing I wanted to talk about is that I feel like in the software world, there are a lot of very well-defined processes and techniques for embedding security into their code. You have things like the Microsoft SDL and so on and so forth. What is a good process for hardware securing? And maybe it's what you've seen, or maybe it's something that you think should be implemented. What are some good processes and techniques in your opinion? Like I said, it could be something you've done before or something you think is on the horizon. So, anybody want to take a stab at that?
Somebody hold the mic.
So yes, as someone from Microsoft who has dealt with the SDL and the lack of a hardware SDL, and also dealt with products that need to be very secure at the basic level, and other ones which are not as critical to be secure or are just open, I'd say it definitely helps a lot to have feedback between security teams and product teams, and we have regular syncs while developing products throughout the entire development process, to get feedback as early as possible and integrate it into the current design.
So a lot of red teaming and feedback given back.
Yeah. Mm-hmm.
I think still the main thing today that's missing is the fundamental educational components around it, right? Mm-hmm. The average hardware engineer doesn't know what a threat model is. And so, but, once you get them ramped up on adversarial thinking, teaching some tools and techniques, especially cross-proliferation with secure coding practices and the like, which can be pushed down, and then maybe augment it with some tools that assist with reasoning, you can get pretty far. But it requires a mental shift, which I have to admit I find hardware engineers are more reluctant to do than software people.
Yeah.
I think they'll get there. I mean, there was a time when software people would say, well, why would anyone do that? And rarely do we hear that anymore. And getting the same adversarial mindset where you start saying, well, they could do anything, and then saying, all right, so let's make a threat model and say what's in scope, what's not in scope. That when you start teaching that and people start doing it, it's really not that hard. It's merely developing a few skills and practicing them. You can ramp yourself up to learning these things relatively quickly. And having adjuncts, people who work with the team from one end or another, helps a whole lot.
Why did you say that they seem to be more reluctant?
Because they're still using shitty languages designed in the late 80s. I mean, it's a field rife with people who don't want to learn new things, in my personal experience, right? Like, we have a whole new generation of hardware design languages over the past decade, which are 100 times better than System Verilog. And to the closest approximation, no one in the world is using them. And that's just telling. I mean, part of it is momentum. Part of it is a mental model they get coming out of university, getting really good at one thing, and that's what they do for their whole career. But I hope it evolves. I hope it changes, especially as we see the boundary blur between software, firmware, and hardware.
Just one thing to add to that. So I totally agree about the old languages, and I don't really see that changing. But recently, there's been uprising of like open source tooling, for like Yosis and whatever. But so it's still Verilog, but I think it'll probably be the thing that leads the way towards wider adoption of better languages.
Yeah. In fact, there's a whole DARPA program on this topic that's trying to bootstrap open hardware development. It's called POSH. POSH stands for Posh Open Source Hardware, of course. And it's been running for the past year and a bit, and we're going to see a bunch of open, high-end IP coming out. You know, maybe in 3 or 4 years, we'll be able to have a full OpenStack laptop, for example.
I think one thing I'm excited about is if you can get the interest and change the mental model, the tooling and the formality around hardware designs is much better than in the software space. So, the number of people that are doing formal verification of their hardware designs is much higher because of the processes and costs involved. I don't know about you all, but when I've talked to software teams about formal verification, it's not that common. So
most of them don't know what it is.
So there's a lot of opportunity there. I think it could accelerate very quickly.
Yeah. Plus, a hardware system is a closed model. You can reason about it. I mean, we have formally verified CPUs in my office. It's a thing,
Yeah, and one other thing to keep in mind is that hardware, once it's baked in there, you can't change it, unlike software. So you have to get it right the first time. It's worth investing in.
Yeah. Outside of the 60 microcontrollers in a modern Intel CPU that are reprogrammable.
I heard the number's much higher than that, but
yeah. Pick your variant.
Cool. So we kind of touched on this answering the last question, but can the security teams and the design teams be the same team, or do they have to be separate?
I've seen effective organizations use both structures. Okay. I think it's an organizational model thing from my point of view.
Yeah, I would say combined makes a lot more sense. Blurring the lines, cross-pollinating, at least iterating between the two teams can speed up hardening of a design and get a lot of security bugs out of the way faster. Otherwise, in a lot of ways, it's like building a binary and handing it over to someone and saying, "Is this secure? Please make it secure." And it's much harder, and you're maybe not going to accomplish your goals in the same way. So that should be avoided.
So I think the teams can maybe be intermixed or whatever, but I think, probably biased, but the people tend to have different mindsets about how they approach problems. So I'm not sure it's realistic to expect people to be doing both jobs 100% of the time. So definitely just have like a nice feedback loop, but don't expect hardware devs to suddenly become people who are going to be breaking their own designs all the time.
Well said. Okay. Sort of switching gears here a little bit. I have a question here, which is, what are the most pressing threats to protect against? And I know that's sort of dependent on use case and threat models, but what are some of the things that you've seen as the things we really need to fix before moving forward with other sorts of threats on the hardware side?
So something that's kind of obvious to me is scalable attacks. I care about, for example, the environment, civil liberties. If you can scale an attack that can damage either of those, or life safety, like self-driving cars, these are things that absolutely deserve our attention. It's hard to think of other things that show up, but there probably are.
So less about the vector of attack, but more the consequence of the attack. Yeah.
I'm worried about food supply, grid, dams, nuclear power reactors, etc., full of SCADA systems with no security and accidentally on the internet.
Yeah.
That's what I get paid to worry about.
Yeah.
I think access to the things we have that are good is also something we need to pay attention to. We've solved some problems reasonably well, but the future is not evenly distributed in this case. And so solving that problem for the vast majority of people who may be in more dangerous situations than those who do have access to it is something that's near and dear to my heart.
I mean, imagine if every airplane were as secure as an iPhone. They aren't, by the way.
Good. Sounds like there's some consensus around that question, so we'll move forward. Another slightly open-ended question. So, what criteria do you use to measure security, and how do you know you're done and ready to deploy? I think Robert's ready to go.
Robert, when you're ready.
Yeah, sorry. Because I've been for almost 10 years a hardware pen tester, breaking into chips, breaking hardware products. And so I have a lot of, you kind of get this feeling like, oh, this product, it wasn't fully baked. Or these guys, it's done. They've really covered everything. And there's this whole gray area in between where it covers the security that it's supposed to. So you think of the threat model, you think of the due diligence on the areas that don't necessarily need to be protected so well. There's a certain point where they're not going to be attacked in the ways that they're expecting to be attacked, and it's very unlikely that other attacks are going to appear. And that's when it's close enough. But again, it depends. For something that is security critical, you have to close all the gaps that you possibly can. And I think security is relevant to everything. So there's nothing that should just be left open anymore.
I agree with that. And I think it goes back to some of the previous questions, because if you say start with a cross-pollinated team, and you have security people and hardware people. And the way that I look at it as, think of it as you're putting together a band and you have people who play different instruments, and you say, gosh, it would be really nice for us to have a good rhythm guitarist, and I'd rather not make the bass player learn how to play rhythm guitar. So you have somebody who comes in, you do a threat model. And part of the threat model, phase one is you list your threats. You say, here's what the threat is and here's what we're doing about it. That if you rank them in terms of how easy would it be to pull this off and how much of a threat is it to the system, things that are easy to pull off and really dangerous are things that if you didn't do them, you're not done. And as a group, you go through and you look at these things. You're going to have to ship with stuff that you don't want, because nothing is ever done. You can't make it perfect. It's not going to be perfect. And you look at it and you have other mitigations, which will include things like, can we change this in the field? Mm-hmm. You can't change transistors in the field, but you can change code in the field. When I was building BlackPhone and we were looking at it, we said, oh my God, how are we going to ship an Android phone that our version 1.0 is not laughably insecure? We said, well, it's a phone. We can do over-the-air updates. So the very first thing that we built was over-the-air updates. And the thing that we probably spent the most intense effort on was over-the-air updates. Yeah. Because if you can over-the-air update the phone, you can let something that you say, I don't know how much of a problem this is going to be, you can let it out the door because you can fix it in 48 hours. And that's a very different situation than something else where if you have said, if we get this wrong, it's the entire device and potentially even the entire company, then you spend a lot of effort on that one. And having those discussions is how you figure out when you're done. And going to the other parts of your company to say, here's our assessment, here's what we think. Do you want to accept this risk because they're going to have to accept some risk or not? Mm-hmm. Then that's where you make the decision when you're done enough to ship.
Yeah, building on that, when you not just have a threat model, but when you believe your threat model, mm-hmm. and when you believe that the things that you've done to address the threats in that model are reasonably complete, and when all of that has been tested in the field, and you still believe your threat model, that feels done to me. As long as you're innovating, that is a process. It's not a done thing. Hardware has to go out at some point, but mm-hmm. I think taking the time to make sure you really believe that threat model and you've covered it is when I feel comfortable enough.
And to kind of add to that, when you have a certification that you're approaching for security specifically, that's also very clear-cut. Okay, you're done. And, you've had, for example, a third-party lab come and attack it, put in a certain amount of effort that the industry thinks is acceptable. And in cases where, for example, I wasn't able to break a product, I would have to justify very thoroughly why it wasn't possible. And at that point, I as an analyst would feel very confident. Like I threw everything I had at it. It still didn't break. Great job. And as an attacker, as a hacker, that hurts your pride. But it has to happen sometimes.
Mm-hmm. Got it. So there's a lot of subjectivity based on how confident you are and how thorough you feel like you've done a job with testing these sorts of things and making it over there updatable
and also saying ahead of time, this is what we think is important, so that when you get to the end, you aren't moving the goalposts and decide that, well, it's good enough. That if you said ahead of time, these are the things that are really, really important, and you didn't get there, then you have the hard conversation, which could be anything from delay, update, cancel the product.
Ship it. Yeah, absolutely. Good. Awesome. Let's see. Are there any myths that you want to dispel when it comes to hardware security, either to this community or to, let's say, the hardware design community that doesn't know about security?
Does anyone think hardware security is easy to do? All right, that's...
Blockchains help with nothing?
Blockchains help with everything.
Depends on, am I stating a myth or a truth? Raise your hands. In my last talk, I made a statement about the myth that nationally critical infrastructure is secure.
Yeah.
A lot of people think that's true. It's not. Yeah. Including DoD systems and the like. The military put up drones that didn't have a cryptographer that vetted the protocol. It's that kind of craziness happens, you know, even in those sorts of systems.
I think the biggest myth I see in the hardware design space is that people assume if they're working for one of the leading chip manufacturers or architecture design houses, then people can't touch them just because they're really advanced, and everyone's going to go after the low-hanging fruit, which is definitely true. But in 2 or 3 years, when your product is used in some space you didn't intend it to be, then it's going to get hacked, just because people have caught up in the meantime.
I think in the same vein that there exists perfectly secure hardware. I mean, you can have things that are very secure and things that are less secure, but it depends on your needs and it depends on your threats. There's no silver bullet here, just like there isn't in the software space.
Yeah, and Joe, feel free to debate me with this, after this panel, but that the formal verification is bulletproof Because for a long time I thought it was unbreakable. And then I found out the models are flawed, and you can still do a whole range of attacks outside of what's been proven.
Formal verification is a tool in the toolbox that one should use. It is not the be-all, end-all of anything whatsoever, especially if you're using a formal verification tool for hardware, which I'll note, they will never tell you what it does or document how it does what it does, nor make any claims about the claims that it makes to you. So don't reverse engineer your hardware verification tools unless you get paid to do it.
All right. Nice segue into the next question. And I think, Joe, you spoke about this a bit during your talk, but what kind of tools are missing from the current landscape for hardware security that may improve it?
Well, I mean, DARPA's funding development of hardware verification tools, like Tortuga's tool, originally came from government funding.
Thanks, Joe. I'll give you your $50.
Yeah, you got the plug. I think there is a enormous gap. There are many enormous gaps in the hardware verification market, or even a hardware assurance market, when it comes to security. We've only seen a nascency of those in the software universe after 20 years of effort, and it was only through sort of major, impactful, but small-scale projects at the likes of Microsoft about 20 years ago that we suddenly saw the gas turned up on that. So I think we'll see the same sort of thing here. Maybe RISC-V, in the way that it's being tackled, will cause a shift in attitudes and the evolution of new toolings from the main vendors that have authenticity and that actually have an impact. I don't think we'll see it, though, in tackling blockchain. I'll keep throwing that out there.
Anybody else? What's missing?
Just a little bit. So
more than two companies that do side channel analysis.
So there is that. I really like the DARPA projects and Tortuga. I believe that those tools are trying to solve important problems that are still kind of open problems, so I'm very excited about those. Actually, I think simulation, as you mentioned, side channel, fault injection, that's a major academic area as well. So I know people are trying to come up with solutions. I do think those tools need to be spread out a bit more and adopted.
Cool. Great. So I think I have 5 minutes left. Is that? So I have a lot of other really good questions that I have here, but I think we'll skip it and go on to Q&A. Does anyone have any questions for any of these folks? And it could be directed at one person. It could be directed at the whole panel. Whatever you'd like. Yes.
When you guys touched on this, what is your vision of what an open source hardware control would be like? And how in your mind does that impact, for example, someone identifies vulnerability that's in the field and can't just easily update or swap out?
So the question is, what is our perspective on what an open source hardware would look like, including finding a vulnerability that's out in the field that can't be updated? Do you want to take that first, Joe?
I would say it doesn't look like what we have today, firstly. Like, if you go to open cores or, any of the open hardware sites, it's just, piles of undocumented stuff with no test bench, no verification case, no docs, etc. I would hope that it would be something where, because of the threat of having something in the field have a lack of assurance or a major vulnerability, that it would be more mature. We could learn the lessons of the high-end systems and software engineering discipline, meet the needs of the open hardware community. And some of it will just be stuff thrown together, Arduino or whatever, and not have any assurance to it. But if you're going to pick a DRAM block and you're going to use it, you should have some assurance around it before you put it out in the field, even if you're doing your own fab. So I'm hoping it'll be more mature. And by virtue of the investment we're seeing from the likes of DARPA and IARPA, that's like $100 million going towards open hardware over these 4 years, which should bear some fruit.
Yeah, I think these DARPA initiatives are just a catalyst that's accelerating this to the point where everything becomes accessible. which is amazing. A few months ago, I read the Hardware Hacker book by Bunny, where he has a whole chapter about this open laptop, which was this kick-ass Swiss Army knife kind of tool. And I've always wanted to build something like that. And between, I guess, some research from Invisible Things Lab or some points Joe Fitz also, like it's really hard to make trusted hardware, especially if you're just a consumer. And FPGA is a good approach to doing that because you can build whatever you want, and it's hard for an adversary to anticipate and control that. Of course, you have to trust the EDA tools. So, and one of my personal recommendations, I guess, is Raspberry Pi. You know, the trust on that is not securable, and so it's a pretty well accepted, fairly transparent platform. Once somebody recovers the netlist, we can actually verify what's going on, and then we'll have a little more confidence.
Got it.
It's kind of similar to what you're saying there. We don't know in many ways what we don't know. I mean, we have specialists, many of them here, that have seen inside of some of these advanced security designs, but the conversations around those things are very closed. So I think we'll know a lot more about what we don't know when you don't get points for your common criteria certification because of not telling people things. Now, I'm not a devout believer that with enough eyes, all bugs become shallow, because we've seen it helps, but it doesn't make things perfect. But I think we'll see some network effect from that. So I'm excited about those things. But to also build on what you're saying, building secure things are hard. Even if you have a piece of secure hardware, the supply chain component of it, and I think Joe did a talk some time ago about the same thing. Like, is this a NAND gate or is it not? Like, you really don't know. So this stuff boils down to, like, if I have a secure hardware design and it is formally verified and it doesn't have any bugs in it, well, I manufacture it at some outsourced fab and they have to add things to it in order to make it testable. What else did they add to it? How could I know that? Those things are exceptionally difficult.
Yeah, and another not well-known thing is, I guess, DARPA chips. So if you have two chips and one is from a trusted list, and you can kind of run the same computations, do some power analysis, you can figure out if there's hardware trojans. You could try to, yeah.
Anybody done trusted fab stuff? Some of them, a little bit. Yeah, a big problem on matters of fabs. The big problem is that we used to have a bunch of trusted fabs, like where everybody there had clearance, and it was mainly processes and protocols with auditing. And over time, with consolidation and cost, those have all gone away to the closest approximation. And so that's why you're seeing all this spend, in fact, on programs about mitigating adversaries at the fab, is because we can't build anything in a modern process anymore. In any sort of trusted environment. So that's one of the reasons the big guys do that. That's exactly right. That's why they take all the runs, and that's why that's exactly right.
Do we have time for a couple more questions or one question? Yeah, go ahead.
So working with SOCs and relying on
some of the hardware protection features like one-time programmable fuses, tamper protection. I thought that you start with a root of trust that way and you could build from there. And then I took Oliver's training earlier in the week and learned about focused ion beam and the fact that you could put metal back down. How do you protect against something like that, or is there protection?
It depends upon what the attacker can do. If somebody is going to put metal back with a fib or something like that, game over, because they are in fact remanufacturing your chip to do what they want it to do, and you don't have any protections against that. There are mitigations that you could put in place in a lot of things, but it's all a matter of what the trade-offs could be, because anything that you put in place is going to make your own design more complex, hard to test. How do you know that it's actually going to work when somebody attacks it? And, in other worlds, making something that is supposed to work in an emergency is hard. Like, for example, I once did a thing where we had secure operations centers, and they were supposed to fail over from one to another. And we found out that when we tested them, they didn't. We came up with a protocol that the team meeting for each one basically took their own thing offline, and it took us 5 weeks of team meetings before we actually got the failover to work correctly. So, and then periodically you would end up like, once or twice a quarter, you would end up with, well, that didn't work like we wanted. So building something that that the mitigation is going to work is very hard, because you now have to have somebody who's going to essentially red team it in a way. But then you get into the problem of, so what are the rules of hacking? If somebody comes up with some other thing that they would do, was that in scope or out of scope? And this is where, again, we go back to writing down what's in scope, what's out of scope. And part of what you would do, for example, in a threat model is write something down like fib out of scope. Game over.
My clients have adversaries who do these kinds of things. And so for a long time it was game over. That was the attitude. But over the past maybe 4 years, there's been two major programs of record where large amounts of R&D are going toward this topic of, let's say North Korea has a chip we really care about. How do you mitigate that adversary, even when they have all those technologies? So the main approaches that are public are the shield approach that I mentioned in my last talk, which is basically how do you add to your IC the ability for the IC to detect when it's vibrated or when it's up, when high energy goes on it and the like, so that it can essentially blow itself. And then obfuscation techniques, historically logic-based obfuscation techniques. So take a net list, munge it up so that it's hard to understand and reverse engineer. And nowadays, more and more, we're using crypto-based obfuscation techniques, wherein you have definitive hardness properties of the obfuscation, which have no impact at all on behavioral characteristics. The chip still behaves like the chip, but due to the cryptographic obfuscation, it does have impact on like how much area you use, and performance is not uncommon. But if you're willing to pay for that, you can essentially create chips that even in the hands of adversaries in large volumes with lots of expertise, they can't learn anything, which is kind of interesting new field, which I look forward to seeing turn into reality, except in cases where we want to reverse engineer somebody else's chip.
I think many secure MCUs these days have some of those features, but that takes it a step beyond. I'm not confident there'll ever be something that mitigates all of those risks, but I think it depends on the overall system that you're using. Why is that a threat to you? Is it because you don't want someone to sell printer toners, from this morning, or is it that you don't want someone to authenticate to your VPN? In which case, the threat is much different. So you can have mitigations in the broader system for the use case that you have, where when something disappears, that those keys are less interesting, or if they're being used for encryption, you roll them more often so less data is exposed, or you use transient keys, like TLS with ECDHE, and for authentication, you notice that it's gone quickly, it's revoked, so signatures and authentication events are no longer interesting in that case. So you have to look at it in the broader threat model as well.
Great. I think that's all the time we have. This was a really good discussion. I appreciate you guys being on this panel. Let's thank our speakers.